Okay, welcome to the positioning and high-speed counting webinar. I am going to start with high-speed counting since I have a feeling that positioning is going to be a little bit more of a longer topic. And positioning itself is actually pretty simple. So I have a training kit to my right here that will kind of demonstrate everything for me. Um, but it does include a high-speed counter and a positioning servo drive. So this will help a little bit with our demonstration. If you can hear the buzzing in the background, that is actually our servo lock on the training kit. So I will keep that off for now, just so you don't have to hear the buzzing in the background. But we'll start off with high-speed counting. So I'm going to make a new program and select HSC or high-speed counter for PLCS. And I'm going to set my starting address to D200. And the reason for this is the special programs do overlap with each other if you are to select the memory address. So for positioning, I selected D100. This will take up around, I believe, 52 or more addresses starting at D100. So we'd be occupying around D152 and so on. So the same will actually occur for the high speed counter. I believe this takes up around 42, if I'm not mistaken. And we can actually check this because we do need to do that in the buffer memory section. So if we go to the help file and we select CM3 CPU, we can go to high speed counter and select parameters. This will show us kind of the variables that we need to use for our high speed counter when accessing and comparing values. So I was actually mistaken. The high-speed counter can take up to 52 words, and that is because we have a two-channel high-speed counter processor. So first channel takes up 26 words. So everything on channel one goes from D200 to D25, 225, while the second channel goes from D226 to D251. So that will take up 52 words, as you can see, starting at offset 0 and offset 51. Anytime you want to access the second channel, you have to just add 26 to what you want to use. So here in our buffer memory, we can see that the important value we want is the current count value, which is D22 for the higher word and D21 for the lower word. So if we want to actually view the value in a program such as Canvas or SCADA, we would access that with D21 to view the lower end of the word and see the entire count range that we can see. So I'll show that as an example in the ladder logic itself. So what we want to do is head back over to our special function, which is program 2. We want to enable count, and that's really about it for setting the high-speed counter. However, there are some more settings that are important for the use of the high-speed counter. So if you want to use the high-speed counter to do a comparison value, you can actually do that by enabling a comparison output. Latch counting allows you to save it to non-volatile memory. So if your PLC loses power, it will remember the currently counted value to a latched memory register, which I believe are the K registers. I'm not positive off the top of my head, but that is listed. It will be listed somewhere in our new help file, which I will also head over to really fast, is to show the new help file. So this is a work in progress, and even though it is not complete, I can still give out the information for this. So if anything is missed or not covered in this webinar, we can actually show it here in the example. So this is the positioning one, which shows positioning on the CM3, and it will kind of guide me into what I am doing today. So back on the high-speed counter, all I'm going to do is just do a basic counting method, and I can show you how it works uh, in the ladder logic. So I'm actually going to delete that line. Um, and I'm going to use a comparison operator. So I'm going to do a D and greater than. So what this is saying is I'm going to do a double word comparison with the greater than operator. I'm going to do D0 and D2. And we need to go back to the buffer memory. So D221. And then I'm actually going to download this to the PLC. Oops. And I want to compare it to an output such as Y. Since I have a training kit, I'm going to use the actual values I have next to me. So I'm going to do Y25, and this should light up actually 30. Yeah, 25. This should light up a value next to me or a light next to me. I apologize. It's actually in the threes. So I will see this, but in CICON, you can actually see the blue little rectangle there to symbolize that the value is actually written and saved. So I'm going to download this to the PLC real fast. And feel free to stop me at any point if you have any questions. I will do my best to answer them, even though there we go. I'll have the chat somewhere over here. I'll keep it out of the way. Um, actually, I'll just exit that. Um, okay, so now we should be online. Let me turn the PLC on. So we can see the D221 is our actual high-speed counter value. So I'm going to actually move this knob around on the training kit. But we can see that at any point, if D221 is less than D0, so while D0 is greater than 221, let's energize that output Y30 or 3.5. So we can see that 0 is greater than or is less than 28. So that's why we don't see the value on the right changing. But once it's in the negatives, it can change. So I'm going to actually change this to a positive value, such as 5,000. So any point where 5,000 is greater than our currently counted value on the high-speed counter, let's energize the output Y3.5. So if I spin the dial, we can see that once we pass the 5,000 mark, that de-energizes. So that's really the basics of the high-speed counter. Not much more in depth to talk about with it. So that's why I will actually head over to positioning. So I'm going to just delete that. And then we have a new special function here, the positioning one, which you can just do new program. Let me disconnect. Do new program, and then positioning for PLCS. You can just hit OK, and this will pop up. So again, I'm going to be setting the starting address to 100. Since again, the high speed counter takes up 200, and I kind of want to use these lower values to input numbers to mess with the position data, which I'll talk about momentarily. But we have two channels for high speed counter. You can control two axes, so the X and Y for both channels, allowing up to 4 total servo drives or motors to be controlled with our PLCSs. And we control high or low active motors. So for this example, I'll be using a high active. When you load the program, it will show up as NA. We want to set that to high or low active. I said I'm going to use high active, but I'm not super positive on what this actual servo next to me is. So if it does not work, I will adjust that back to low. The bias speed at the start kind of is your speed for an error. So we want to make sure that this is set to have some bias for an error, and I will double check that I have this information correct. And it will actually be listed in a much more user-friendly way on this help file. So here I've actually taken the buffer memory. Let me close out of that. the buffer memory or position data and operation data and have translated it over. Um, One more time, I want to do breakdown, or I want to break down the offsets here. So we have the X and Y axis. Your Y axis will begin at a plus 11. So anytime that you want to access anything, so if you wanted to see the, um, let me see, I need a good example. If you want to see when the OPR operation is completed, for example, you need to do D211 dot C to actually see if that bit is 0 or 1 to see if the OPR operation has completed. The address, you need to do D 112 since we are starting at D0, and the offset is 12 to see the lower word of your positioning address for the Y axis. So I know that's a little bit confusing, but I will explain it more once I get into the actual example and how we can actually use the control flags for moving the motor itself without having to do any special PSTRT or POS CTRL instruction such as this. So I want to head back over here and actually get the bias speed correct. So it's the initial speed of the positioning operation. So when you activate your motor, it will hit this speed for a certain amount of time before it actually hits the full speed that you have selected with your speed limit. Um, Let me double check that I have that. Yeah, so speed limit right here. This is the max value that you can do with your motor. CICON supports up to 100,000 PPS or pulses per second for your motor. And I would double check what your actual servo driver motor can handle before changing this value for the speed limit. But your jog speed is what your motor will actually move at. So I'll demonstrate that right here. Let me download this to the PLC. Okay, so we can see that if I hit jog, and that sound in the background is my motor moving, we are moving at 10,000 pulses per second, and we are actually moving in the negative direction as it is counting down. So this here is our monitoring menu. You can select the X or Y axis up here, and here is the device stands for data register, but here are all of the informational pieces that you want to use if you wanted to know the dwell time, the deceleration or acceleration time, the constant speed, etc. So these are the actual data registers, which all lie in D101, and then use the bits to handle that. You can see your current position is D102 and D103, while your current speed is D104 and 105. And if we change it to the y-axis, you can see the offset of 12 and 13, as I mentioned earlier. When you open this menu, your access will be disabled by default. So you can hit enable, and then you can either jog forward, and we will begin going in a positive direction. To go backwards, you have to stop it, and then hit the backwards button. And now we are going back to negative. If you are moving and hit emergency stop, you will actually cause an error. So the bit F of D101 will be on. To reset, all you have to do is just hit the error reset, and then you can move again. So if you have an error, you shouldn't be able to move the motor back and forth. I want to double check that is okay. So I'm not sure why that's doing that. I have had it before where you can't move it unless you error reset. So that might be just my specific setup. I'm going to move back to the parameters. The acceleration and deceleration time is how long it takes for your motor to hit the jog speed limit. So this is in milliseconds. So we can see that each of the four are set to 1,000 milliseconds, which is equivalent to 1 second. So it's going to take us 1 second to get our motor to 1,000 pulses per second. The software stroke and lower and upper limit is how much your motor can move within the software. So we have the 2.14 billion to negative 2.14 billion to 2.14 billion. So our range is 2 to the power of 32, which is 4 billion unsigned, but we do use the signed notation. So you will be moving from the negative 2.1 billion to positive 2.1 billion. Um, so speed, control, current position. So if we wanted to move the motor and not update its current position value, all we have to do is select do not update current feed value. Update will change the position every time your motor moves and clear current feed value to 0. Each time you start your motor, it will begin at position 0. So if I set this here and we hit monitor, we can see that we are at negative 65,000 is our position. But if I move it after I modify the program, it will reset back to 0. And then again, it takes us 1 second since the acceleration time is 1,000 to hit 1,000 pulses per second. Let me stop that. Backlash compensation amount is just for an error. So if you experience an error while moving your motor, it will backlash and compensate that amount. I know it's a little bit straightforward, but I'll head over here to explain it. So due to an error, um, backlash will occur, shifting the direction. So it's to help correct the motor itself if it experiences an error. As I mentioned, the jog speed high, that is your current speed limit. So you can hear the actual difference depending on your motor. So we're moving it 10,000 pulses per second. But if I adjust this to be 20,000, and I hope the microphone is picking this up, um, we can actually hear a difference. So we are there moving at 20,000 pulses per second. So the jog speed limit can't be higher than the speed limit value itself up here at the top, but it can be equal to it. So if we wanted to change this value, we actually can change it to, 30,000, any value in between 0 and 200,000, as it mentions it down here. So I was incorrect. CICON can handle a speed limit of 200,000 pulses per second. So that can also be the same value as your speed limit. The acceleration time is correspondent to these numbers here. So if you wanted to have your value for 3 be equal to 5,000, we can set this value to 3. It will take 5 seconds to reach a jog speed limit of, make sure, 10,000. So we can see it took about 5 seconds to reach that 10,000 value there. And then same with the deceleration time. It takes about 5 seconds to stop. So that's what this value here does. Inching speed. This is how much your motor will move every second. So if we want to do 100, it'll output 100 pulses per second and inch that much forward. So about every second, it will move 100 pulses. And we can see that here. So if I set the inching to 100, we can see that it is moving 100 pulses. And so that value can be changed here or in that menu that I mentioned earlier. The OPR methods here are for original point return or origin point return. It depends on what program you're using, but they both mean the same thing. It is your motor physically returning to its origin or position 0. So CICON does offer it virtually, but to physically move your motor back to 0, you will need the SP32 CPU series. This will allow you to use the dog and OPR sensors to return back to your original point. So if you are using a 16, you can't actually use this method physically, but you can use it virtually. So that kind of covers your parameters. The position data is a little more interesting. So you can have up to 30 different position data for the X and Y axis, and there's different instructions. So what this does is this allows you to use the PSTRT1 for X-axis or PSTRT2 for the Y-axis, and allows you to target these individual position data numbers. So there's a few different control systems. We have ABS, INC, feed, FSC, RSC, no op, jump, loop, lend, or POS. So I'll go into what these are individually. We'll begin with no op. So no op just means no operation. This line will not execute. It won't do anything. It means nothing. The loop, it begins to run everything inside of the loop. So if I do a continuous control, you have to mark the loop with everything in the loop and the loop itself with continuous control. And the operation speed doesn't matter, so that can be one. But the position address is how many times we want the loop to execute. So this should usually be a smaller number unless you want to execute 5,000 times, but that's fine. For this, we can do 5. So everything inside of the loop will execute 5 times. So if I did that and I have another continuous control and I do a feed, it will execute the feed instruction 5 times, and I can set the position address to 5,000. I can input that number correctly. And then line 3 will be a continuous control of end. This stands for loop end. So you need to begin a loop with loop and end it with lend. So what this is saying is we are going to run the feed instruction 5 times. And what the feed instruction does, as I mentioned it earlier, it can reset your position value to 0 and increase to 5,000 each time. So what I'm going to do is head back over to, or I'm going to online modify. I'm going to head back, hit the monitor, head over to the actual ladder logic. So what I have here is just a one-shot contact executing the PSTRT1 instruction. So PSTRT1, again, it's controlling your X-axis. I am targeting the positioning module, which is H000, or the CPU in this case, since I do not have a positioning module on me. D10 is going to be the number of position data I want to execute. So this is a number between 1 and 30, and I want to actually double check that I have this correct. So the instruction for PSTRT should be here. Let me double check that I have this correct. Yep. Okay. So D10 again is that number that we want to target. So this is currently 0. However, 0 is not going to work. We need a number between 1 and 30. What I'm going to do is I'm going to target number 1. And then here is just the position or the error for D0. So that number is not important. But what we should see here is the motor going to starting at 0, moving to 5,000, and doing that 5 times. And it is technically doing that. But what I want to do is change the operation speed here to be 1,000. So it is doing that at a speed of 1. So it is going to take 5,000 seconds to actually reach that value. So I'm going to stop the motor and then online modify. And I'm going to execute the instruction one more time. So we can see that it will go up to 5,000 and it will go back to 0, go to 5,000, and go back to 0. So we'll do this 5 times, and I will run it through just to make sure. And then we'll stop at 5,000. So that kind of covers loop and feed at the same time. So again, feed will begin your position at 0 and go to the position address at the amount of time defined by operation speed. For the next example, we will do ABS. Set this to single step control. I'm going to change the ABS position address to 10,000, change the operation speed to 1,000, and I will demonstrate how this works. So this is going to move to 10,000 pulses and stop. So no matter where our motor is, I believe that the ABS instruction will move us to that position. So if I want to actually get rid of the inching there, so we're going to move. And we are now, as you can see, moving back towards 10,000. So no matter where your position is and you run the ABS control code, it will move us back to 10,000. So as you can see here in another 5 seconds, we'll be back to 10,000 as our position, and it will stop like that. The next control code that works kind of in conjunction with that is the INC instruction. What this does is it moves us in the direction 10,000. So I will online modify, and you can see if I run the PSTRT instruction here, it will move to position 20,000. If I was to run it again, it will then move to 30,000. If we wanted to move backwards, all we have to do is just put a negative in front. I'm going to change that operation speed to be 2,000 so it can go faster. So online modify. We will run it, and we should see that we end up at 20,000 pulses. And that's the INC instruction. So ABS gets us to that absolute position that we want in our address, while the INC or increment instruction gets us that many pulses for our position. The next two that go together are FSC and RSC, or forward speed control and reverse speed control. What I'm going to do here is change this to 10,000 and then modify, monitor, move back here, run it again. So this will just keep us moving in the forward direction. And there is no way to stop it, so I need to actually press this button here. And if I wanted to stop it with the actual bits, I can show you how to do that momentarily. RSC will just move in the negative direction, or reverse speed control. So if I target that and run that, you can see we are now moving in the negative direction as this value here is decreasing. I will stop that there. And the last one is POS, which I'm not super familiar with, so I want to actually double check what I'm doing here. I believe it will start us at that position. So if I run this, yes, okay. So POS gets us to the position that we want. So if I change the position data to be 100,000, so I'll change it to be 500,000 so that it shows a different number. Online modify. I run it, we now begin at 500,000 pulses. So that is kind of the basics of the control systems. Again, ABS gets us to the position that we want, while INC moves us by the position address. Feed will get us to the position address, but starting at position 0. FSC and RFC will move at the operation speed, so it ignores the position address. No op will be a no operation. Jump, which I didn't demonstrate, will it works like loop. It will jump to another position data number. So if we had jump and then the target address of 10, it will jump us to 10 and begin doing the operations at position data 10. Loop will run a continuous loop specified by the position address amount of time. End signifies the loop end, while POS or position gets us to begin at the position that we want defined by the position address. So the last thing that I want to cover is if we go back to the buffer memory, we can see that we have the control flags here. We can actually target these individual bits to have our motor move, stop, enabling the X and Y axis, and so on. So what I want to begin with is D0. So, or D100, as there is an offset. What I'm going to do is do I believe we'll just do a coil. So we'll do 100.0. And then turn that off. Monitor. Okay. So you can see that this button here is enable, which means our access, in fact, is disabled. So if I enable it with the enable button, that is actually not working. Let me use a different instruction. I'll do RST D100.0, and I will do another M1, do S set D100.0. Let me double check that this works. Okay, so we need to use that instead. We can then see that the access itself is enabled, or if this value is 1, we want to disable it. We just activate the RST instruction, and it is now disabled. And we can see that here, the enable and disable access. If it is set to 1, the access is enabled. If it is set to 0, the access is disabled. And I will actually reiterate that one more time with the memory monitor. We can go to D device, hit device bit. And as you can see, I will enable the access. So at 100.0 or D100, which I'll scroll down to. D100 bit 1 is turned on. Then I can go back and disable it, and it is now 0. You can also change it here in the memory monitor itself. So if you wanted to enable, we can head back over here, actually disable that. And we can now see that the access is enabled. If we wanted to control the access itself with the jog instruction, we can do that by targeting the individual coils. So what I want to do is target D103 to move it forward and D104 to move it backwards. Sorry, D100.3, D100.4, and then D100.1 to stop it. So let me edit that. Add a few lines here. We'll do M. We'll do 2. Target D100.3. Do M3. Target D100.4. And then M4, we will target the 100.1, and I will add the last two. So if we target D100.2, we can do the emergency stop request. And if we target 100.f, this will reset it when enabled. So I can show that with an M5, D100.2, and then M6, D100.f. So by doing this for these examples, the jog forward and jog backwards here will rely on the parameter data. So if I set the speed here to 15,000, we should hear a difference in the motor next to me, but we should also see a difference in the position. So if I head back here and I enable the coil D100.3, it is moving slowly. Let me double check why. I would like to stop. Let me try changing this to a low active. So the motor itself is actually inching forward, which I'm not super positive on why it is doing that rather than jogging. It could be the configuration that I have on the motor itself, um, which is what I'm going to go with. Unfortunately, I can't fix that at this moment. However, I will continue to demonstrate. So we can actually see that if we jog the motor forward, it is moving at 100 pulses per second. And if we try to reverse the motor, we actually do end up with a confliction here. So if D100.3 and D100.4 are both on at the same time, neither will happen or the last one active will happen depending on when you activate them. So as you can see, neither are moving now, but if I reactivate the reverse, we are moving backwards at 100 pulses per second. So if I head back to the buffer memory, again, 100.3 is to move forward, 100.4 is to move backwards. But the safest thing to do is to turn on 100.1, which is to stop it, as you can see right here, and then begin moving backwards again. Stop it, reactivate the forward, and we're moving forward. Lastly, for moving forward and we activate 100.2, we should error out the device bit itself, 100.2 will error this entire offset. And to fix that, all we would need to do is turn this off, reset here with F, and we should be good to move again, as you can see. So again, I apologize with this little example here on why it's not showing that we are actually not inching or moving at 100 pulses per second. I can't fix that at this moment with the current configuration, but hopefully that helps you guys a little bit more with understanding positioning and high-speed counting. I know high-speed counting, again, was pretty short, but it is a lot simpler of the two, while positioning has much more in-depth information. So I will conclude the webinar here. If you have any questions, I will stay in the chat for a moment.